All right, let's jump right into this explainer. We're looking at a fascinating paper from June 2026 by Xiaoqu Zhang and team, and it's all about a massive breakthrough in AI coding assistance called FastContext. Now, if you follow how AI is changing software engineering, you already know we've kind of hit a wall when it comes to navigating massive, sprawling code bases. But, well, this paper presents a really elegant, highly structured solution to that exact problem.
So, let's start with a really simple but honestly kind of perplexing question. Why do incredibly smart coding agents completely fail at relatively simple tasks? You drop the most advanced AI into a massive, unfamiliar code repository, and suddenly, it's just stumbling in the dark. As it turns out, the issue isn't that the AI lacks logic or coding skills. No, the problem is fundamentally about how it looks for information.
To get to the bottom of this, we'll just break the research down systematically. First, the context clutter problem. Second, introducing FastContext. Third, how FastContext actually works. Fourth, the performance boost. And finally, the future of coding agents.
Okay, Section 1, the context clutter problem, when searching ruins solving. For any developer using large language model coding agents right now, repository exploration is just a massive headache. The crucial concept here is context pollution. Basically, this happens when irrelevant code snippets from exploratory searches completely clutter up an AI agent's memory. It fundamentally degrades the model's ability to solve the actual task. It's literally like a master chef tearing apart a messy pantry to find one specific ingredient, right? By the time they actually find it, the kitchen is an absolute disaster, and they've completely forgotten the recipe they were trying to cook. The AI gets so overwhelmed by the sheer volume of code it just read, it totally loses track of the bug it's supposed to fix.
And naturally, this context pollution leads directly to a massive token budget drain. See, in most current agents, the exact same model is tasked with both exploring the repo and solving the task. It's doing double duty. This means all those exploratory reads, all those dead-end searches, they're left sitting right there in the solver's history. You end up wasting a massive amount of your precious token budget on completely irrelevant code snippets. For us developers, that means the process is expensive, it's really slow, and it hopelessly confuses the AI.
Which brings us to Section 2, introducing FastContext, a dedicated exploration subagent.
This perfectly illustrates the paradigm shift the researchers are proposing. On the left, you've got the traditional setup, one giant model doing the exploring and the solving, polluting its own history along the way. But contrast that with the FastContext architecture over on the right. The team realized something absolutely crucial. Repository exploration can and absolutely should be separated from problem solving. By delegating the search to a highly specialized subagent, FastContext, the main model's memory stays completely pristine. It literally only sees what it absolutely needs to see to write the code.
Moving on to Section 3, how FastContext works. Precision on demand.
The workflow here is wonderfully simple, mapped out in these 3 steps. Step 1, FastContext is invoked on demand by the main agent. It doesn't just run wild, it waits for instructions. Step 2, it issues parallel tool calls to search the codebase incredibly fast. And Step 3, honestly, this is the magic part. It returns concise file paths and specific line ranges as focused context. So FastContext acts like the perfect sous chef. It jumps in only when needed, searches multiple areas at once, and hands back the exact ingredients, just the file paths and line numbers, instead of dumping entire bloated files onto the cutting board.
Let's peek at the specs for the models actually powering this. The paper details that these dedicated exploration models are right-sized, spanning from 4 billion to 30 billion parameters. They're bootstrapped from strong reference trajectories, which basically means they learn from the best search patterns out there. Then they're meticulously refined with task-grounded rewards for one very specific job: broad first-turn searching and multi-turn evidence gathering. They are built to find exactly where the relevant code lives and then generate a precise citation. By specializing the model, you're getting a tool that's just far more efficient at finding a needle in a haystack than a generalized coding model ever could be.
All right, Section 4, the performance boost, benchmark results.
To actually prove their theory, the researchers integrated FastContext into the Mini-SWE-Agent. And they didn't just test it on a handful of easy toy problems either. They ran it across 3 major rigorous industry benchmarks: SWE-bench Multilingual, SWE-bench Pro, and SWE-QA. They really needed to see if completely separating the search from the solver held up in real-world, highly complex repository environments.
So, across those rigorous benchmarks, the end-to-end resolution rates jumped by up to 5.5%. Now, I know 5.5 might sound like a modest number at first glance, but in the world of complex software engineering benchmarks, a 5.5% absolute gain is huge. It proves beyond a shadow of a doubt that a cleaner context directly leads to smarter problem solving. When the AI isn't bogged down by irrelevant code, it just writes better fixes.
But honestly, even more staggering is this metric: 60. The integration of FastContext drove a massive reduction in the coding agent's token consumption by up to 60%. Just let that sink in for a second. 60% fewer tokens used, with only a marginal overhead to actually run the subagent. Because FastContext is only returning precise file paths and line ranges instead of entire files, the main model reads dramatically less text. For the end user, that means faster generation times and significantly lower API costs, all while actually improving the quality of the code being written. It's a total win-win.
Finally, Section 5, Future of Coding Agents, the Era of Specialization. As the authors, Xiaoqiu Zhang and team put it perfectly, repository exploration can be separated from solving and handled effectively by specialized models. The researchers basically proved that forcing one massive general-purpose LLM to do absolutely everything, from digging through folders to writing the final function, is fundamentally broken. It's inefficient, it's expensive, and it's incredibly prone to context pollution. The future really lies in specialized, delegated AI teamwork. Smaller, highly refined models do the prep work, so the massive models can focus on the heavy lifting of actually solving the problem.
As we wrap up this explainer, I want to leave you with this thought to ponder. How will specialized subagents change the future economics and capabilities of AI software development? I mean, with up to 60% token reductions and much cleaner, faster problem solving, we aren't just looking at a minor efficiency tweak here. We are looking at a fundamental shift in how we build, deploy, and scale AI developers tomorrow. It is a really fascinating look into the very near future of software engineering. Thanks for joining me for this explainer, and stay curious.